Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss deaerators and steam systems, generation of steam in boilers and boiler feed water preparation. The one thing that almost all process and chemical plants have in common is steam. Steam is almost universally used to transfer energy over reasonably short distances, that is, less than a mile, for the following reasons. Steam has a high latent heat of condensation. This permits flowing steam to transmit about 8 times more energy than that transmitted by a pound of butane. Steam is non-explosive, and hence reasonably safe to handle. Steam is generated from water, which, while not free, is often inexpensive to obtain. Steam is used for several purposes in a modern process plant. To spin turbines. To provide process heat, mainly to reboilers and preheaters. As a stripping medium in fractionation towers. To increase the velocity of heavier liquid streams, typically in furnace tubes. As a lift gas, to lift heavier liquids or solid catalyst streams to a higher elevation. As a purge medium, to prevent pressure taps and other instrument connections and relief valves from plugging. If energy for either motive or heating purposes must be transmitted over long distances, that is, more than a few miles, it is best to use electricity. The energy loss, due to both friction and ambient heat. Radiation is orders of magnitude greater for steam as compared to electrical power. Most electricity is produced from steam by use of a steam-powered generator. Typically, it takes 3 BTU of steam to generate 1 BTU of electricity. That is why it is best to use the steam directly, at least for heating purposes, if the distance between the boiler house and the consumer is small. Boiler feedwater and its sources. Steam is generated from boiler feedwater. But water used for steam generation must first be purified. For example, raw water drawn from the river has 3 objectionable contaminants: sand and silt, dissolved solids, typically carbonates, oxygen. The particulate matter, sand and silt, is removed by flowing upward through a gravel and sand filter bed. The coarser gravel is in the lower part of the bed. The filter beds are backflushed periodically with clear water to clean off the accumulated mud. The dissolved solids, such as calcium carbonates, are removed by hot lime softening or demineralization. Demineralized water, also called deionized water, typically has essentially all anions and cations removed by ion exchange resin. Demineralized water is preferable to hot lime softened water as boiler feedwater for several reasons. For one thing, steam produced from hot lime softened water will have some amount of silicates. These silicates tend to deposit on the rotor blades of turbines, which use the motive steam as a source of energy. The silicate fouling of the turbine blades reduces the turbine's efficiency. But, more importantly, from an operator's point of view, the silicate deposits eventually break from the blades. This unbalances the rotor. An unbalanced rotor is the fundamental cause of vibration. Vibrations lead to damage of the shaft bearings and seals. Eventually, vibrations will destroy the turbine's internal components. Also, the hot lime softened water has variable amounts of carbonate contamination. When boiler feedwater is converted to steam, the carbonate deposits will break down into carbon dioxide and hardness deposits. The hardness deposits coat the inside of the boiler's tubes, interfere with heat transfer and overheat the tubes. The carbon dioxide, which is also generated from the dissolved solids, creates more serious corrosion problems in downstream heat exchangers. When the steam condenses, the carbon dioxide may remain trapped in the reboiler or preheater as a non-condensable gas. Actually, there is no such thing as a non-condensable gas. Even CO2 is somewhat soluble in water. As the CO2 dissolves in the condensed steam, it forms carbonic acid, a relatively weak acid, pH typically between 5 and 6. Strong acids will have pH values of 1 to 2. Pure water has a pH of 7. Carbonic acid is corrosive to carbon steel heat exchanger tubes. Oxygen is a particularly reactive element. Actually, oxygen is a very potent gas and reacts aggressively with exposed metal surfaces to form oxides. Of all the corrosive substances encountered in a process plant, few exceed oxygen in reactivity with steel pipes. If a considerable amount of oxygen is left in boiler feedwater, interior corrosion of the boiler tubes will be rapid. The bulk of the oxygen, or dissolved air, is stripped out of the boiler feedwater in a deaerator. In properly operated process plants, most of the boiler feedwater should be recovered condensate, that is, when steam condenses to water, the condensate produced should be recovered and returned to the boiler house. Often, the recovered condensate will first pass through a deoiling clay bed to remove any hydrocarbon contaminants. To calculate the percent of condensate recovered, we need to know two numbers. Total steam production, SP. Total raw water flow, RW. The percent condensate recovery, CR, can then be calculated. CR equals 100% minus 100 times RW per SP. Plants with CR greater than 70% are usually doing a good job of recovering condensate. CR values of less than 30% represent poor performance. Poor condensate recovery is expensive for two reasons. One reason is the energy and chemicals needed to prepare the boiler feedwater. However, in recent years, there is a second, more expensive cost associated with poor condensate recovery: effluent wastewater treatment. I well remember one refinery in which boilers and heat exchangers suffered from constant steam-side corrosion and fouling. Investigation showed that the intake water treatment plant operators would occasionally partially open the raw water bypass around the entire treatment plant. They had a good reason, however, which they explained: you all have to admit, some kind of water is better than no water at all. Deaerators. This picture is a sketch of a typical boiler feedwater deaerator. The lower portion of the deaerator acts as a surge vessel for the boiler charge pump. The working part of the deaerator is the smaller vertical section on top of this surge vessel. The vertical section is essentially a small, 4-tray, steam stripper tower. Sometimes these trays are called mixing shelves, but their function is the same as any distillation tower tray: to bring the vapor, steam, into intimate contact with the liquid, soft water. The objective of the little tower is to drive off the light component, air, dissolved in the soft water, with the heavier component, steam. The deaerator shown in picture is operating at 250 degrees Fahrenheit. This particular temperature corresponds to the boiling point of water at 15 psig. We can say, then, that the temperature of the deaerator controls its pressure. However, it is equally correct to say that the pressure of the deaerator sets its temperature. The 120 degrees Fahrenheit soft water is heated to 250 degrees Fahrenheit by the 50 psig heating steam. In most deaerators, the vast majority of the heating steam is condensed inside the deaerator. The heat of condensation of the steam is used to heat the soft water. Usually, only a small amount of the heating steam, specifically, stripping steam, is vented through the restriction orifice located in the atmospheric vent. It is this small stripping steam flow that drives the air out of the soft water. Note that the collected steam condensate does not pass through the little stripper section. As this stream is just condensed steam, it should be free of air. Hence, it does not need to be stripped. A common deaerator malfunction. Mr. X was once a high school teacher in a school. I do not quite understand the connection, but many high school teachers become good process plant operators. Perhaps they find the work less hazardous. Mr. X became an operator at the utility complex for a major sugar refinery. Here is a rather neat problem that Mr. X and I solved together. The problem was cavitation of the high-pressure boiler feedwater charge pump, as shown in picture. Such pumps are often multi-stage. This means that there are 3 or 4 pump impellers on a relatively long shaft. The longer the pump shaft, the greater the damage caused by vibration to the pump support bearings and mechanical seal. Cavitation is certainly the leading cause of vibration in centrifugal pump operation. The cause of cavitation in this case was loss of liquid level in the Deaerator surge or water storage vessel. The symptoms of the problem Mr. X described to me were as follows. 1. An operator working at the main boiler would open the boiler's blowdown valve. Some lime-softened water, about 10% of the boiler's total feed water, must be drained to maintain the total dissolved solids, TDS, content of the boiler's circulating water below a safe maximum. 2. This would draw water out of the deaerator vessel. 3. The level in the deaerator would fall, and the flow of 120 degrees Fahrenheit soft water into the deaerator would increase. 4. Suddenly, the flow of softened water would increase exponentially. The level control valve would rapidly open. Yet, the level in the deaerator would slowly continue to fall until the pump lost suction and cavitated. Mr. X and I then made the following field observations. 1. When the flow of softened water exceeded 80,000 pounds per hour, the heating steam pressure control valve, as shown in picture, would open to 100%. 2. A further increase in softened water flow drove the deaerator pressure down. This happened because the deaerator temperature also dropped. 3. Suddenly, the atmospheric vent pipe, which had been venting steam, started to blow out rather large quantities of water with the steam. 4. This removed some of the water from the boiler feed surge drum portion of the deaerator. 5. As the deaerator water level fell, the 120 degrees Fahrenheit softened water flow increased. 6. The escalating flow of colder softened water cooled down the deaerator. 7. Since the water in the deaerator must always be at its boiling point, the reduction in the deaerator temperature resulted in a reduction in the deaerator pressure. 8. The reduced deaerator pressure coincided with an increase in water jetting out of the atmospheric vent. What was happening? Well, we have already discussed this phenomenon in a previous video on tray flooding. Water carryover from the top of tray 1, as shown in picture, is simply a clear signal that our little 4-tray distillation tower is flooding. But what is causing the trays to flood? Trays usually flood because of excessive vapor flow. The vapor flowing to tray 4 is essentially the heating steam flow. Certainly, most of the steam condenses on the trays, as the heating steam comes into contact with the 120 degrees Fahrenheit softened water. It takes about 1 pound of 50 psig steam to heat 7 pounds of water from 120 to 250 degrees Fahrenheit. The uncondensed steam is then vented from the top of our tower through the atmospheric vent. However, the full steam flow, from the pressure control valve, does flow up through tray 4. Obviously, when this pressure control valve is 100% open, the weight of vapor flow to tray 4 is at its maximum. However, dear listeners, do not forget that when the steam inlet pressure control valve is 100% open, any further increase of cool softened water flow will suppress the deaerator's pressure. When the pressure of a vapor goes down, its volume goes up. Volume is inversely proportional to pressure. In addition, when the volume of a vapor flowing through a tray increases, so does its velocity. Any increase in vapor velocity through a tray result in higher tray pressure drop. Moreover, what is it that causes trays to flood? Why, it is high tray deck pressure drop. To solve this problem, Mr. X recommended to his boss that the softened water be preheated by using it on one side of a heat exchanger to cool off a waste-foul liquor stream that was flowing to the effluent treatment pond. This heated the softened water from 120 to 160 degrees Fahrenheit. The 50 psig steam demand was reduced by 25%. This reduced steam flow prevented the trays from flooding. Note that it is okay to heat softened or demineralized water to 160 degrees Fahrenheit. You should not, however, do this with raw water. Calcium carbonate salts will plate out and foul the heat exchanger tubes. I rather like this problem. It illustrates how knowledge of one type of process equipment, a distillation tower, can help us understand problems in a piece of equipment that is superficially quite a bit different. Boilers. A rather typical boiler is shown in picture. This is the sort of boiler one might rent to generate 50,000 pound/hour of 150 psig steam. Incidentally, rented process equipment does not have to be returned to the owner if the plant files for bankruptcy. But that is another story. The boiler shown in picture relies on natural circulation. The density difference between the water and steam in the downflow pipes and the riser pipes causes the water to circulate through the pipes. A typical circulation rate results in 10 to 15% of the water flow being vaporized into steam. The produced steam flows from the steam drum into the steam header. The makeup boiler feed water valve maintains the water level in the steam drum. A certain amount of water is drained from the mud drum. The amount of this blowdown is determined by measuring the TDS in the steam drum. Typically, a target of several thousand parts per million, ppm, of TDS is specified. If the steam is generated at a low pressure, 150 psig, for use in reboilers, rather high TDS may be acceptable. If the steam is generated at a high pressure, 1400 psig, for use in high-speed turbines, a much lower TDS target would be set. It is really the quality of the treated boiler feedwater that sets the blowdown rate. Deionized or demineralized water might require a 1 to 2% blowdown rate. Hot lime softened water might require a 10 to 20% blowdown rate. The amount of hardness deposits and silicates in steam is a function of entrainment of water, as well as the TDS of the boiler feedwater. A well-designed boiler, then, often is equipped with a mesh-type demister pad to remove entrainment from the produced steam. The water level in the steam drum in picture controls the boiler feedwater, BFW, makeup rate. However, note that the steam drum is full of boiling water. How can we measure the real level of this two-phase mixture in the steam drum? After all, the external level indication chamber, level troll, holds just water. When we look at the gauge glass, it has water, not steam. Hence, the indicated water level outside the drum is less than the boiling water level inside the drum. This discrepancy causes water carryover with the steam due to high boiling water levels. If we are superheating the steam, then the silicates and other salts in the entrained water will deposit inside the superheater tubes. What I have just described is the leading cause of superheat tube failure. Most of the trouble can be avoided if you understand that the actual level inside the steam drum is higher than the external water indication shows. I have explained this matter in greater detail in the video on waste heat boilers. Superheaters and economizers. This is not a complete picture of a larger industrial-type boiler. Mainly, it does not show the superheat and economizer tubes. This picture gives a better idea of the relative arrangement of the steam-generating tubes, superheat tubes, and economizer tubes. Let us assume that we are generating 100,000 pound/hour of 150 psig steam. In the economizer section, the effluent from the deaerator at 250 degrees Fahrenheit would be heated to 350 degrees Fahrenheit. As the specific heat of water is 1.0 BTU per pound degree F, we would need 100 BTU per pound of water. However, to produce 100,000 pounds of steam, we might need a 10% blowdown rate to control TDS. This means 110,000 pound/hour of boiler feed water is needed. Therefore, the economizer heat duty would be 110,000 pound/hour times 100 BTU per pound equals 11 million BTU per hour. The latent heat of vaporization of 150 psig steam is roughly 880 BTU per pound. Therefore, the steam generation section heat duty would be 100,000 pound/hour times 880 BTU per pound equals 88 million BTU per hour. The specific heat of steam is 0.5 BTU per pound degree F. As shown in this picture, the saturated steam will be superheated from 360 to 680 degrees Fahrenheit. Alternatively, we may say that the steam superheat will be 320 degrees Fahrenheit. We would then need 160 BTU per pound. Hence, the superheater section heat duty would be 100,000 pound per hour times 160,000 BTU per pound equals 16 million BTU per hour. The total boiler heat duty would be the sum of the economizer, generation, and superheat sections, or 115 million BTU per hour. I have noted that the stack flue gas temperature of the boiler is 680 degrees Fahrenheit. Let us assume that we have around 3% oxygen in the flue gas, or about 15% excess air. We can then apply the following rule of thumb. For every 300 degrees Fahrenheit that the flue gas temperature exceeds the ambient air temperature, the boiler efficiency drops by 10%. If our ambient air temperature is 80 degrees Fahrenheit, then our boiler efficiency is 80%. The fuel consumed in our boiler is then 115 times 10 power 6 BTU per hour divided by 0.8 equals 144 million BTU per hour. Waste heat boilers. Probably only 20% of process plant operators or engineers ever work on the sort of boilers shown in pictures. However, 90% of process plant personnel will, at one time or another, in all likelihood operate a waste heat boiler. In many petroleum refineries and chemical plants, most of the plant's steam is generated in such waste heat boilers. One of the most common such boilers is the kettle boiler, as shown in picture. The hot oil to the kettle boiler is a circulating pump-around stream from a fluid catalytic cracker fractionator slurry oil circuit. There is a fundamental difference between this sort of boiler and the utility plant boilers discussed previously. In the kettle boiler, the heating medium is inside, rather than outside, the tubes. To obtain the full capacity of the kettle boiler, the uppermost tubes should be submerged in boiler feedwater. This requirement creates a few problems. First, note the water level in the level indicator shown in picture. It looks quite a bit lower than the water level inside the kettle. Why? Well, because the water inside the kettle is boiling water. The water density has been reduced by the bubbles of steam. I have discussed this problem in detail in my video on level control. Basically, the difficulty is that the water in the level indicator has a specific gravity of about 1.0. The boiling water in the kettle has a specific gravity of perhaps 0.5. If we have 4 feet of boiling water in the kettle, then, by pressure balance, we will have 2 feet of cool water in the level indicator. To compensate for this problem, the top tube of the tube bundle should be kept well below the top of the kettle. This also will help retard entrainment of boiler feedwater in the steam. To further improve the steam quality, the experienced design engineer places a dome, as shown in picture, on top of the kettle. The dome will have a sloped demister mesh pad. A demister acts to coalesce small droplets of water into larger droplets. The larger droplets easily settle out of the flowing steam. The demister is sloped to promote liquid drainage from the surface of the pad. Of course, if the steam from the kettle will be used to reboil some nearby column, entrainment is not a major problem. If the steam is going into superheater tubes, however, serious entrainment will lead to solid deposits inside the superheater tubes, and this may cause these tubes to overheat and fail. Fouling of turbine blades would also result. Identifying waste heat boiler tube leaks. This picture shows 2 waste heat boilers that are generating superheated, 150 psi steam from a fractionator hot oil pump around. After years of trouble-free operations, water was observed in the gas oil pump around return stream. The symptoms of the water infiltration into the fractionator were an increase in the fractionator pressure and an increase in the water production from the fractionator reflux drum's draw-off boot. The operators planned to bypass boilers A and B in turn, as shown in picture, to determine which boiler had a tube leak. Boiler A was arbitrarily selected. The hot gas oil pump around from the fractionator was closed. With the reduction in the gas oil pump around heat removal, the generation of 150 psi steam dropped in half, and the water intrusion into the fractionator stopped. The operators concluded that with waste heat boiler A out of service, and the water leak into the fractionator apparently eliminated, the leaking boiler was A. However, when boiler A was hydrotested by the maintenance department, no leak was found. So, boiler A was returned to service. But, as the operators restored the flow of gas oil to boiler A, the indications of water intrusion into the fractionator returned. The operators, quite angry, again removed boiler A out of service and insisted that the maintenance department this time find and actually fix the tube leak in boiler A. This scenario was repeated 3 times, until the plant manager intervened and instructed the engineering department to purchase a new $250,000 tube bundle for boiler A. The refinery had lost $100,000 per day in production for about 40 days, up to the day that the new tube bundle arrived. The new bundle was quickly installed. As the gas oil pump around flow was restreamed, the flow of water into the fractionator was once again initiated. Can you see the problem? It is a failure in applied logic. Boiler A was never leaking. All along, it was boiler B that leaked. Here is what had happened. When boiler A was removed from service, the steam flow from the steam drum dropped by 50%. The delta P through the superheat coil, shown in picture, dropped from 30 psia to 1/2 square times 30 equals 7.5 psia, that is, delta P varies with the flow squared. The pressure in the steam drum then fell from 180 psig to 150 plus 7.5 equals 157.5 psig, that is, the pressure of the 150 psig plus the superheat coil delta P. The pressure in the steam drum fell below the 160 psig pressure of the gas oil pump around return. The leak of water into the gas oil stopped. The leak reversed and became a small leak of gas oil into the steam drum. Whenever boiler A was returned to service, the extra steam flow repressurized the steam drum above the pressure of the gas oil and thus restored the water leak into the gas oil. It was found that the steam was contaminated with gas oil whenever the waste heat boiler B was in service with boiler A offline. Boiler A was put back online again and the water reappeared in the fractionator as it had on the 4 prior occasions. However, we now had boiler B isolated, but left boiler A online, with no resulting oil contamination of the 150 psig steam and with no water contamination of the gas oil pump around. A tube leak was found and fixed in boiler B, and then boiler B was also returned to service and the full unit charge rate was restored. An intelligent engineer solved this problem in just 4 hours, while the client failed to solve the problem in 40 days. One key observation he made was the oil contamination of the steam at the steam sample point shown in picture, when only the boiler B was in operation. The second observation he made was that the steam drum pressure increased above the gas oil pump around pressure, when both boilers were in service together. This story illustrates the importance of making direct field observations. The relevant pressure gauges and samples were not available until the engineer showed up on site and asked that they be installed. It also illustrates an even more important principle of taking an analytical approach to problem solving. That is, all possible contributions to a problem need to be considered. Then field observations should be made to confirm or refute the existence of each problem. Convective section waste heat steam generation. This picture shows another common form of steam generation from waste heat. Boiler feedwater is circulated, via a pump, through the convective tubes of a fired heater. Most of the heat released by the fuel, 50 to 70%, is absorbed in the process coils. Perhaps 10 to 25% of the waste heat in the flue gas is absorbed in the steam generation coils. It is good design and operating practice to keep the percent of water vaporized in the steam generating coils to well less than 50%. Higher rates of vaporization promote the laydown of salts inside the convective tubes. Low water circulation rates will lead to tube leaks. It is probably best to consume steam generated in small waste heat boilers locally in steam reboilers and preheaters. Turbine drivers are best powered by boiler house steam, where steam quality is more closely monitored and controlled. That's all, gentlemen. If you like my video, Please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.